All right, so I have a question regarding the half-life problems. So I'll go ahead and get started on that since it doesn't look like anyone's here for the live stream quite yet. So specifically, I was requested to, make sure I'm looking them up wrong, problems 1, 3, and 5, and 7 if possible. So let's just start with 1, 3, and we'll go from there. So I'll bring these up for you. First question, what is the half-life of oxygen-19 if only 22.3 grams of 25.6 grams of the sample is left after 2.53 seconds? So the half-life formula, pretty straightforward formula. Number equals the starting amount, 1/2 to the t over t sub 1/2. Now, the N here is just the number of atoms. It can also be mass, it can be moles, it can be anything simply because these all scale by a proportionality constant, meaning that if we start with atoms, we can convert that to moles using Avogadro's constant, but that'll be on both sides, and we can convert the moles to mass. So really, N can be any quantity as long as we're consistent on both sides of the equation. So, in this problem, sorry, I gotta bring it back up. We finished with 22.3 grams. We start with 25.6 grams, and the time it took to make this happen was 5.23 seconds. So now we want to figure out what the actual half-life is. So to do this, we're going to move things over. So we get 22.3 over 25.6, and we're going to, for me, I prefer to take the natural log. You can do logarithms. It's going to give you the same, basically the same answer when you're done. Just for me, it's more natural work with the natural log, but this is the ln of one side. We'll do the ln of the other side, and by the property of logs, if we have a number raised to a power when we take the natural log, it's just the number we're raising to, we're going to move it over. So now we've got natural log 22.3 all over 22.3 divided by 25.6 divided by the natural log of 1/2. This equals 5.23 over t sub 1/2. So now we need to solve for the 1/2. The easiest way to do this, multiply the t 1/2 over and bring this other part over. So we get t 1/2 equals 5.23 divided by natural log 22.3 divided by 25.6 divided by the natural log of 1/2. So this is just more algebra than anything else. You've got your formula and you just need to rearrange it to isolate the variable that you're interested in. So in this case, you should end up getting about 23.6. So question 3, what is the starting mass of cobalt 60 at the half-life is 5.2714 years and only 18.58 grams of the sample is left after 12 years. So again, starting with our half-life formula, we know we're going to finish with 18.58 grams. We want to know how much we started with. It took 5.2714 years. And, oh, sorry, that's the half-life. It took 12 years. We started with 5.2714. So to solve for the starting mass, it's just 18.58 divided by 1/2 to the 12 over 5.2714 power. Now the other questions, 5 and 7, are basically just isolating different variables. Again, this is going to kind of take the same approach. Put the numbers you know into the formula, and then start isolating back out the variable you want. In the notes, I give two forms of this equation. So one form is this form, the other one is natural log over n naught over the natural log of 1/2 equals t over t sub 1/2. That's just this equation rearranged with the natural log, that's it. So really, those are the only two formulas that you really need to work with for the half-life formulas. So next question, can you go over NERT's homework number 2? Bring it up. So in this equation, I'm going to write it up on the board behind me. I've got H2O plus HBr plus cobalt goes to bromide and cobalt hydroxide. And you're given 0.005 molar sodium bromide, 0.200 molar HBRO, and your pH equals 4.55. So in order to figure out Q, we just write out an expression for the reaction. So Q is the concentration of bromide over the concentration of HBRO. So these numbers are given to us. Bromide comes from our sodium bromide, so this is 0.00500 divided by the concentration of the HBRO, which is 0.200. And you will get a number from there. pH is given to you to see if you're actually paying attention or if you're just trying to fit every number you see in the problem into the equation. pH would show up here if we had H plus or OH minus in our reaction. Because we don't, you should only, for any reaction, you should only be using the information relevant to Q or for the reactions you're working with. So since H plus and OH minus don't show up in the equation, that pH is irrelevant. There are several electrochemical reactions that are completely independent of pH because it doesn't show up in the equation. Converting acidic to basic conditions. So given the following reaction, HNO2, reversibly going back and forth, H plus and NO2 minus 1. And we want to know how this would change our equilibrium constant KQ. So specifically, we're looking at what power we would raise Kw to, Kw being the equilibrium constant for water. So the equilibrium constant for water, H2O, goes back and forth to H plus and OH minus. So if we want to cancel out the H plus, we're going to need to subtract this reaction. So that will flip us to, we'll switch colors, the flip version here is H plus OH minus goes back and forth to H2O. So if we add the negative of this to this, our H pluses cancel out, and this gives us basic conditions. So if we subtract a reaction, this ends up being Kw to the negative 1. This is the same thing as K1 divided by Kw. So A in this case is negative 1. That's what you would be raising the Kw to. As far as more or less favorable, easiest way to approach this is just to look at Le Chatelier's principle. So if we have acidic conditions, the H plus is on the right. If we switch to basic conditions, we're basically removing this product. We're removing all the H plus from solution, which will drive the forward reaction. So we would consider this a more favorable reaction. Can you go over number 2, oxidation states? Yes, you're welcome for the help. Jacqueline, you're welcome for the help. Number 2. So give the oxidation states for each of the components of this. Now, books teach this differently. Instructors teach this differently. I prefer to use an equation simply because I think it's a bit more intuitive. You have a relationship to solve it with. So this is much more of a Chemistry 1 concept. There are comments in the notes, but the idea was that you learned about oxidation states when you learned about how to name metals with nonmetals in Chemistry 1. So the way I teach oxidation states is that there are rules and there are guidelines. And the rules always have to be followed, whereas the guidelines are meant to be good guesses in the absence of other information. So there are really only a couple of rules when it comes to oxidation states. The first is that the sum of the oxidation states has to equal the charge on the molecule. So if we add up the oxidation states of all the atoms, here we have carbon and 3 oxygens. This has to equal the charge here, -2. Now, a common misconception is that this -2 says something about the atom is beside. It's not. This -2 is across the whole molecule. So you can't use that -2 to imply what the oxidation states is. You need better judgment. But again, the first rule is that if we add up the oxidation states, we have to get the charge of the molecule. The second rule is that the more electronegative element has to take the negative charge, and as a similar line of reasoning, the less electronegative element has to take the positive charge. So oxygen is the most electronegative, so it's going to be negative. Carbon is the least electronegative, so it's going to take the positive. But that's as far as our lines of reasoning can go. So the next step are guidelines, and guidelines can be violated. So let me bring up a periodic table. So what the guidelines are going to do is that they're going to assume that elements want to be isoelectronic with a noble gas, meaning that they have the same number of electrons. So you can either memorize the guidelines or you can rederive them. So if we go to the periodic table, fluorine, chlorine, bromine, iodine, acetine prefer to be -1 because one more electron would make them look like a noble gas. Oxygen, sulfur would prefer to be -2. Nitrogen would like to be -3, +3, or +5. Boron, aluminum, gallium, indium, thallium, these all act like metals. They like to lose 3 electrons to go back to noble gases. Beryllium, magnesium, calcium, barium, strontium, barium like to lose 2. Lithium, sodium, potassium, rubidium, cesium, francium like to lose 1. Scandium, yttrium like to lose 3. Zinc and cadmium like to lose 2. So those are our guidelines. Now, before I go too far, carbon can go either way. It can lose, actually, it can take any oxidation state from -4 to +4. So we don't really have a guideline for carbon. Now, it is reasonable to assume in this case that oxygen probably went to -2 because it's not competing with itself for electrons. So the only time oxygen is not -2 is when it's in a peroxide and it's -1, or when it's bound to fluorine, which will end up giving it a positive oxidation state. So if we guess that oxygen is in a -2, then we have the oxidation state of carbon plus 3 times -2 equals -2. So carbon plus -6 equals -2. So carbon here is in a +4 oxidation state. Now again, we can break the guidelines. So this guess that oxygen is -2 doesn't necessarily have to be obeyed. But we do have to obey the rule that says because oxygen is more electronegative, it's going to be the negative element in this compound. Because carbon is the least electronegative, it's going to be positive. So we could guess -1 for oxygen. It's just not a reasonable guess because it is bound to carbon and it is big enough ability to pull away all the electrons it wants from carbon. Okay, so go back to Nernst equation number 2. And the question is, how do we end up adding 0.73 and 1.33 for the standard reduction potentials? So let me write the reaction back up. So I'm guessing that this one probably comes from the tables of standard reduction potentials that are found on the course website. Again, I don't like, it is the oxidation reaction minus reduction minus oxidation. So E cell is that. So what we're going to need to do is actually look up these potentials. And I'm guessing I probably use the ones in the tables found on the course website just to kind of like give us more options. The final exam is a lot more focused, but it is kind of limited in terms of the examples we can do. So if I look at the bromide reaction, HBRO goes to Br minus, this is 1.311 volts. And we have cobalt is negative 0.28. So we just use this formula. First we have to identify the oxidation and reduction reactions. So bromine here is going from +1 to -1, so our reduction reaction is the 1.331 volts. The oxidation reaction is this negative 0.28. So we have 1.331 minus negative 0.28. Negatives end up canceling out, so we end up adding them together. So we get 1.611 volts. I'm sorry, I looked at the wrong reaction. It's cobalt hydroxide. So sorry to bring that back up. Main reasoning is still the same. So the cobalt to cobalt hydroxide is minus negative 73. So instead of minus 0.28, it's minus 73, but it's still going to end up being plus 73 when we add it, because the minus and negative will give you a positive. So that'll give us the 2061, which is what the key is, 2.06. So the big thing here is you're subtracting a negative, so it ends up adding it. But the actual potential of that reduction reaction is minus 0.73 volts. But because you're running the oxidation reaction in reverse, because what you're working with are reduction potentials, so it's the voltage to reduce it, but this is an oxidation reaction, so the voltage would be the reverse of that. Since you're reversing the reaction, you reverse the voltage. So E-oxidation will always be negative. Not necessarily. There are several reactions that you can go through that table that they are positive voltages as written, but if the reaction is being run as an oxidation reaction, we're going to flip the sign on it. There are some reduction reactions that are negative, and when we flip them, we'll get a positive. But as far as the actual signs on the oxidation reduction reactions, that depends on the elements. Some elements don't like being reduced. So if you look at something like, I'll bring back up the table here. If you look at something like sodium. Come on, where are you? Nitrogen, neodymium, here we go, sodium. Sodium here has a negative reduction potential, minus 2.71. So that reduction reaction is going to be negative. The oxidation reaction of sodium would actually be 2.71. So sodium going to sodium plus 1, that's favorable. If we look at something like fluorine, EFG. Fluorine going to fluoride, that reduction reaction is 2.886 volts. The oxidation in that case would be negative. So it really depends on where you are on the periodic table. Generally speaking, but not always speaking, metals will have a negative reduction potential. Non-metals will have a positive reduction potential, but that makes sense. If you're reducing, you're gaining electrons. Non-metals tend to be more electronegative, so they like to gain electrons, which makes that favorable, which gives you a positive voltage. Metals like to lose electrons, which is the opposite of reduction, so you expect the reduction to be a negative voltage, it's unfavorable, and the oxidation to be positive. But again, there's exceptions to this. Particularly when you work with transition metals, there's like weird intermediate oxidation states where they would prefer to be in one oxidation state but not the other. So you're just going to kind of have to rely on a table. Generally speaking, for the Nernst equation, we're only working with batteries. And so we prefer to end up with a positive voltage. This is not universally true, but for the problems you're working in this class, your Nernst equation should finish with a positive voltage. If you get a negative voltage, it's because you're running your battery either backwards or you're doing electroplating. Yeah, you're welcome. All right, other questions? There should, so in terms of just the normal weekly announcements, it should be up there. But as far as updates, I don't think there's really any new updates this week. But let me just make sure. Yes, the normal weekly announcement. I don't really have any other updates. Now, Blackboard has been acting kind of weird because this is the first time in like a few weeks I've actually gotten the announcement saying my announcements have gone out. But I haven't got one of those in a while. I'm still seeing it on Blackboard. Like on my end, I'm seeing that it's showing that the announcements are visible. But for some odd reason, it's just not sending me notifications anymore that an announcement has been sent out. So if you go to announcements, it should be visible as, it's down the list, but it should definitely be visible. So let's see. So in my version of the student view, welcome announcement, live streams, week 6-1. How odd. Because if we switch back to my view, it says that this was posted. How very odd. Yeah, on my end it's showing that the announcement has been posted and the only restriction was the date. It's also not showing previous announcements as well, which it should be doing. So yeah, I see your confusion, because as you can see on my end, like, it's not visible when I go to the student. Well, hold on. Let me check one more thing about the student view. Yeah. Wow, that's so weird. So it's showing all the announcements except the one that should be visible this week. So tell you what, let's take a look at the adaptive release. This is not the first time it's done this to me. And again, for me, every time I log into Student View, I have to take the course entry quiz to see anything. So you have to give me just a minute. Yeah, that's so weird. It should be showing you that announcement. Because there's week 1, week 2, week 3, week 4, week 5, week 6, week 7, and there should be week 8 sitting right there. So let me contact Blackboard and figure out what's going on. But yeah, on my end, it's showing that it's visible, but I'm not seeing anything else. Now, as far as your question, do I need to complete anything for the new course intro due tonight? You shouldn't need to complete anything. As far as I can tell, that's mostly, I mean, we used to get emails about it. Honestly, it just sorts to my junk folder at this point. But you shouldn't need to do anything because you're already enrolled in the course. That said, if tomorrow you log on and is giving you issues, shoot me an email just so I know and I can give, like, we can make accommodations if there needs to be. But you shouldn't need to do anything with the new e-learning. It's mostly just there for students. I'm guessing it's new for the fall, students coming into the fall, which will be in like 4 or 5 weeks. But yeah, you shouldn't need to do anything about it. Excuse me. You're welcome. Study guide. So question about the oxidation states. If you're talking about the chromy ones, those are supposed to be both +6. And I don't know why that it doesn't say +6 for both of them. So yeah, if you're talking about the chromate and the dichromate, they're supposed to be both chromium +6. I don't know why it says +4, +3. This is definitely a new development for me on this bracket. But the plan, I've updated it on my flash drive. I just haven't loaded to the course website yet. But for CR04, to show people what questions I'm talking about, this should be chromium +6, and this should be chromium +6. I say it's new because these packets are like 2 years old, and that should have been caught by now, so I don't understand how that ended up being +4 and +3. But you are correct, it is +6 for both. Yeah, you're welcome. Yeah, I've updated it, I just haven't loaded to the course website yet. Basic solutions from redox equations. So is this a homework problem or a packet problem? Lab right now. So the nice thing about balancing redox react, so we'll do number 2, and I don't know if number 2 is going to be the same for you that it is for me, but we'll see. So in this case, it's asking you to balance the nickel chloride. I'll write up on the board. Nickel +2 plus chloride goes back and forth to nickel plus ClO -1, so chlorides. So the nice thing about these types of problems is you're going to balance them the exact same way you would have balanced a reaction under acidic conditions. We're just going to do the basic as like an extra couple steps. So if we were to go through and balance this reaction, we've got chlorine in a -1 going to a +1, nickel in a +2 going to a 0. So if we write the half reactions, nickel +2 goes back and forth to nickel. Chloride goes back and forth to ClO -2. This is 2 electrons. This is 2 electrons, so we can go ahead and add these back together. So this is already balanced in terms of the oxidation reduction couples. Now we're going to balance the oxygens like we normally would. So we've got one on the right, none on the left, so we're going to add one water. And then we're going to balance our hydrogens on the right side. So this is how you would have balanced it just under normal acidic conditions. Now, to switch to basic conditions, we're going to do 3 steps. First, we're going to, for every hydroxide we have on one side, every H plus we have on one side, we're going to add just as many hydroxides to the other. So if we have 2 H pluses here, we're just going to add 2 hydroxides to the opposite side. It would be true if it was the other side. If we had 2 H pluses over here, we'd add 2 OH minuses over here. The second step is we're just going to convert our H pluses to H2Os. And the reason we do this, the true formal way to do this is to take this reaction and add or subtract it until you get all the H pluses gone through the hydroxide. Well, switching places of the hydroxides and the waters is basically the same overall effect. So step 1, put a hydroxides on the opposite side from the H plus, make sure it's the same number. Step 2, convert all your H pluses to H2Os. And the last step, cancel out any waters that appear on both sides. So we've got 1 water here, 2 waters here, so we're just going to subtract 1 water off both sides. And this would be your balance under basic conditions. 2 OH minus plus Ni plus 2 plus Cl minus goes back and forth to nickel plus hypochlorite plus H2O. And if we look at the key, we get that answer. So I'll switch it back to the desktop. We have our 2 hydroxides, we have our nickel plus 2, our chloride, our nickel, our hypochlorite, and the water. So yeah, balancing under basic conditions, there is actually a procedure for balancing under basic conditions, but the far easier thing to do is balance it like it's acidic, and then do the last 3 steps to switch you from acidic to basic. It is the lab practical time. Let me take a look and see. You get 90 minutes to take the lab practical. And it shows up in the directions. So when you click on it, it will say, there's a big paragraph of information, but it will definitely say that you've got 90 minutes to complete it. You can technically add the 2 OH minuses to both sides, and the OH and the H plus will come together to make water. I just think it's a lot simpler just to put the hydroxides on one side and then convert your H2Os. It's kind of that adding hydroxide to both sides is kind of like extra steps. I understand where that would have come from. Really, the purists would say you're supposed to add the water dissociation reaction and keep doing that until you've got rid of all the H pluses. What I've shown you is just kind of a shortcut way of doing that. As far as the old labs lab practical, yeah, they're going to be very similar. So look over them, make sure you got your lab notebook in front of you and that you're comfortable with what you did. This should not be like a super intense lab practical. It's mostly just making sure you understood the concepts that you covered in the lab this semester. Yeah, you're welcome, Lauren. Yes, you can. So if you want DSS accommodation for the lab, because this is timed, it is possible to do it. This is something we generally can't do for the seated lab section because we have 2 hours and 50 minutes. That's kind of a hard wall on the scheduling. But yes, if you can submit make a DSS request, I can give you the extra time for it. For those of you waitlisted for organic this fall, I'm trying to make a recommendation and see if we can get it in on time to open a 3rd organic section on South Campus for Orgo 1. It doesn't look like Orgo 2 is filling up, which makes sense. Typically, students don't take Orgo 2 at Wake Tech. And I'm skeptical we're going to fill it up in the next 5 weeks. So I'll see if I can convince them. It's really not that much more work on our end to do that. Jacqueline will just shoot me an email to remind me when I get done today to give you the DSS accommodation for the lab practical. I mean, fill out the paperwork for due diligence, but like you are correct. Generally, I don't think about it because when we do the seated lab sections, like it's 2 hours and 50 minutes. The next class comes in, so we can't give you an extension on those types of exams. Like we just physically can't do it. But definitely for an online timed exam, we can definitely give you the accommodation. Oh, looks like you just submitted it. Actually, no, I can't give you an extension because WebAssign will not let me do that. It looks like I can give you an extension on the date, but I cannot give you an extension on the time. So the time itself is hardwired into the exam itself, and it's part of the settings for the exam, but I personally can't override that. The only thing I can do is let you take it at a later time. So I think in this case, this is going to be another one that we just can't get you the DSS time because I can't change the hardwiring on the exam. Basically, it's a property of the exam, the test itself, not actually like something I can change in terms of like scheduling for WebAssign. So sorry about that. Didn't mean to give you false hope. It looks like it's going to have to be done the same way we normally do these practicals, that everyone gets the same time regardless. No, I'm glad I looked into that though. Yeah, I don't think there's a way to actually manually give you the extra time, which is something I can do in Blackboard, but I can't do here. Yeah, you're welcome. Ideally, I'd like to give you the extra time, but this isn't my assignment. It actually belongs to another instructor, and it's hardwired into theirs, so not much I can do on my end. Lab practical is just going to be more of a rehash of old labs, so processing data, understanding how to do the analysis that you did for the previous labs. So kind of like being given the old labs but with data and ask concepts about the data. It's 90 minutes. It's not meant to be like a full repeat the experiments, more of an analysis of the data itself. So that's what you should expect with this practical. How do you prepare for it? Let me see. Let me make sure I'm not telling you what to do first. In the 3 minutes that remain. To prepare, my best advice would be make sure you got your Excel sheets that you used and anything you did for the data processing handy. So just to kind of expedite your ability to grade to process the data. Again, a lot of this lab practical is looking at processing data and looking at concepts. So it's not going to be the pre-lab that helps you so much as it's the post-labs that you did for your lab reports. That said, nothing on this lab practical should be completely out of lab field. Like, it is very much based on the labs you've done. So yeah, have your lab notebook handy and have your Excel sheets handy, and that should kind of help you out quite a bit. All right, so we're coming up in the last minute here. Again, reminder, everything's pretty much due to Thursday night at midnight. So all the lab stuff, all the homework stuff. The goal is Friday morning to download everything off the course website, calculate your lab grades, get those posted, get your homework grades posted, get your quiz grades posted. So this way you'll know this weekend more or less what you need to get on the final exam in order to get the grade you want in the course. Now, if you've decided, hey, I just want to drop out of the course, that's fine. Shoot me an email. The plan is Thursday to start processing all the withdrawals or any that I've received. Basically, if you want to withdraw the course, I'll just claim the last day you showed up was Monday. That's fine. But once you take the final exam, or once you start the final exam, you've automatically completed a grade in the course. I'm also not going to withdraw you just because you don't take the final. So if you don't take the final, I'm just going to give you a 0 on the final, and that'll be your grade. So if you do plan on withdrawing, let me know so I have that documentation. But again, the plan is to do the withdrawal paperwork Thursday, just to go ahead and get those knocked out, because that'll also kind of be the last day of attendance that I have to enter until the final exam. Your final exam grades, again, the earlier you take it, the more we can talk about your grade. But if you take the final exam Monday, and you don't get the grade you want, there's not much I can do for you, because Monday I need to have the grade submitted. I'm not going to really have time to look over questions about grade boosts. So again, good luck. Get everything done Thursday, and the goal is Friday to get everything up for you, so this way you've got a good idea as to what you need on the final exam. And I will see you all tomorrow. Thanks for showing up.